Now that we know how to calculate the pH of just about any solution there is, we want to take a little bit of time to talk about the acidity of salts. So one of the first ideas in acid-base chemistry was this idea of neutralization reactions, that you would have an acid, it would react with a base. And this Bronsted-Lowry definition is based around this idea. And so if you react an acid with a base, kind of the generic description of what that looks like is you have water and salt, a salt, as your product. And so you're always going to get this water as one product and a salt, which just means an ionic compound. So what we want to talk about is what's going on with these salts. So one of the things when we talk about this neutralization, a lot of times we kind of normally think about it as strong acids and strong bases where we go to completion. One of the important things to consider or remember is that even when you do a reaction of a weak acid with a weak base, that weak designation only is describing the reaction of that thing with water. Say acetic acid and ammonia, both weak, when they react together, the equilibrium constant is 3.13 times 10 to the fourth. So that's what, 31,000? You can actually get it in general. It's Ka times Kb divided by Kw. And if you remember, Kw is 10 to the negative 14th. So anything that is weak, when you divide it by 10 to the negative 14th, you're going to get a big number. So most acids and bases, even if they're weak, when they react to completion, and you can use stoichiometry, and you're going to be making these salts. So, and if you put a strong acid as one of your reactants, the reaction will definitely go all the way to completion. And so you're definitely going to get a strong reaction. So whenever you do these reactions, you're always going to get salts. So one of the questions about like what salt acidity is the question of what is the acidity of a solution after you do a strong acid and strong base neutral, and any acid base neutralization. So if I do a neutralization reaction, say HCl plus NaOH, and now I'm going to make water and a salt. And so if I want to know the acidity of the resulting solution, it's based on the acidity of the products. So H2O, that's not an acid, not a base. Water does not affect the pH of water. For KCl, we know that this is an ionic compound, and ionic compounds dissolve into separate ions. So if we want to parse out what the acidity of a salt is, of this ionic compound, I need to know what is the acidity of each ion in my solution. So each ion can affect the pH of a solution, right? You can have the cation can affect the pH and the anion can affect the pH. So collectively, both of them may or may not have an effect on the pH, and you can classify any salt as acidic, basic, or neutral. And those basically imply if you add the salt to water, does it decrease the pH? Then it's acidic. Does it increase the pH? Then it's basic. Or does it just not affect the pH, which would be a neutral salt? And so this is really important because we can use salts, we dissolve salts in all sorts of solutions, trying to do things like make any sort of solution where you're dissolving ions into it. You can do things like affecting colligative properties, trying to make an electrolyte solution. And if that's all you want to do, you maybe want to pick a neutral salt that you're not going to be affecting the pH. We've seen basic salts before. Our stereotypical strong bases are the metal hydroxides, the group 1A, group 2A metal hydroxides, so sodium hydroxide. When you dissolve that into water, it just is hydroxide, so it is a base. Beyond hydroxide, we are generally looking at salts that would react with water to produce hydroniums or hydroxides. So we'd be looking for things like strong acids or strong bases that are ions and then therefore contained within a salt. So when we're looking for this idea, what we kind of want to do is figure out, is a solution, is one of our ions neutral? And if not, basically, is it an acid or is it a base? So there's a couple of things that can point to something, the kind of tendencies of objects. One of the things we can think about is for acids, generally they need hydrogens. Acids donate an H+, so for the most part, don't worry, there's exceptions. For something to be acidic, it needs to have a hydrogen atom in its molecular formula. Anything that is a cation then cannot be a base. Cations do not function as bases. The reason for that is bases accept H+, cations are already negative. So that would be already positive. So that would be a positive thing taking on a positive H+. that is not going to happen. There's just a lot of resistance to two positively charged things coming together. If you have a group 1A or 2A cation, so the things that are when paired with hydroxide make a strong base, those cations are always neutral. So a lot of the cations you're used to seeing in solutions, things like sodium, potassium, lithium, calcium, magnesium, those sorts of ions that we're used to seeing, those are all going to be neutral because it's just a metal, right? There's no hydrogen, and they're cations, so they can't be an acid or a base. The other thing that cannot be a base is anions that are conjugates of strong acids. A lot of times when we see anions, we should probably be thinking those are maybe bases. There are 6 anions, though, that are not bases. It's chloride, bromide, iodide, nitrate, hydrogen sulfate, and perchlorate. So these 6 anions, their conjugate acids are the strong acids. And if you remember, the conjugate base of a strong acid is just not a base, right? Weak acid is conjugate with weak base. So weak and weak are paired together in a conjugate, but a strong acid, its conjugate just is not a base. Because the strong acids are so good at donating away H+, their conjugates just can't take it back from hydronium. So we do want to be mindful, HSO4-, it's not a base. The rest of the things on this list are all neutral. So these other 5 things are all neutral because they're all anions. They have no hydrogen. That can't be acids, and they're not bases. But HSO4- is a weak acid. So we do want to be careful. That's a tricky one where that is a weak acid. It is not neutral. It's not a base, though, like most anions are. Most anions are weak bases.
Let's do some examples. Classify the following salts as acidic, basic, or neutral at LiBr, lithium bromide, NH4I, ammonium iodide, NaCH3COO, sodium acetate, and Rb2SO4, rubidium sulfate.
So we want to identify salts that can be acidic, basic, or neutral. And in order to do that, really the main part of that is figuring out what the ions are. We know that these are all salts, so they're going to separate out into the individual ions, and then we want to diagnose each ion. Each of the ions can potentially be acidic, basic, so on. So if I have LiBr, we know that it's going to cut, I have a cation and the anion. So what I'm dealing with is Li plus and Br minus. So I want to figure out each of those. So I'll start with lithium. Lithium is in group 1A. So it is an alkali metal. Because this is in group 1A, a metal cation, we know it's going to be neutral. One of the things we could think about is, can it be an acid? Well, it has no hydrogens. So it has no hydrogens. This thing cannot be an acid. Okay, so this cannot be an acid. It's a group 1A cation. It's going to be neutral. No hydrogens means it's not an acid. Cation means it's not a base. Bases attract H+. This thing already is positive. So it's not an acid. It's not a base. Group 1A means neutral. So lithium isn't going to affect the pH of the solution. What about bromide? Well, it can't be an acid because there's no hydrogens. So it's not an acid. Okay, so we know it's an acid. So then it is an anion. And anions can be bases. All anions can be bases. So in order to figure out if it is a base, we want to think about the conjugate. So in this case, my conjugate acid is HBr. And HBr is strong. We have our list of 6 strong acids. HBr is on there. Hydrobromic acid is a strong acid. Because the conjugate acid is strong, that means Br minus, bromide, is not a base, right? In order for it to be a base, the conjugate would need to be a weak acid. But because HBr is strong, that means Br minus is neutral. So the lithium is neutral, the bromide is neutral. Overall, this salt is neutral. NH4I is ammonium iodide. So I have NH4 plus and I minus. So NH4 plus. The fact that it's a cation leads to this thing is not a base. So one of the things we want to ask is, well, is it an acid? Well, it has hydrogens. Has NH4 plus, has hydrogens, and so we would think that's maybe an acid. And actually, ammonium ions, we can see if we look on the weak acid chart, NH4 plus, that's 5.6 times 10 to the negative 10. It's a pretty weak acid, but the H's lead to this thing being an acid. One of the things we can also kind of think about is if we think about the conjugate base is NH3, which is weak. And so if the conjugate is a weak base, that means it itself is a weak acid. When you have weak acid, the conjugate's always a weak base. So when you're dealing with strong things, the conjugate is not. So in the case, HBr is a strong acid, so the conjugate bromide is not a base. But in this case, if the conjugate base is a weak base, then this has to be a weak acid. So NH4 plus is acidic. That is an acidic cation. So then if my anion is I minus, well, no H leads to not acid. And then, so we know it's not an acid, it is an anion. So we're going to think about what the conjugate is. Well, my conjugate acid, in this case, is HI, which is strong. That leads to this thing being neutral. So iodide is a neutral anion. We always want to be mindful there are 6 of our, the 6 strong acids. Their anions, their conjugates, are always not bases. So very common to see those. That's actually why we use chloride and bromide as counterions so frequently, because they're neutral. They don't affect the pH. But this thing is acidic. So this thing is an acid. This one was both I minus is neutral, so this doesn't matter. But this, because there is ammonium, ammonium is a weak acid. Any salt containing ammonium contains an acid, and that makes it a weak acid. So ammonium iodide, when you dissolve it, the ammonium behaves as an acid. That salt is acidic. Sodium acetate. I have Na plus, so no H leads to not an acid. And cation leads to this thing being not base. We can also just look and we see, if we see group 1A, that tells us it's neutral. Group 1A, 2A is also the same. Any cations from group 1A or 2A on the periodic table, so, you know, your potassiums, sodiums, magnesiums, calciums, those are all going to be neutral. And again, that's why we use those frequently in the lab. So, you know, when you want to just dissolve a salt into solution, you just dissolve sodium and it won't affect the pH of your solution. It just functions as a salt. You don't need to worry about it being an acid or a base. The anion then is CH3COO minus. This is not an acid. It does have hydrogen, but if you remember, those hydrogens are attached to the carbon, so not acid. But it is an anion. And the anion, you always need to check, is it a base? And you ask, well, what's the conjugate? And so the conjugate is CH3COOH. We've seen that before. That is acetic acid. Acetic acid is a weak acid. This is weak, which means this thing is a weak base. So, yep, this thing's a base. Acetate is a base. This is a basic salt. So if you dissolve sodium acetate into solution, it will be a base. It will raise the pH of solution because you're putting in a weak base. And in all honesty, that's a lot of what weak bases are. Weak bases are anions from a salt. So that's really how you get it into solution. The sodium is just there to be the cation to counter the negative charge. You can't make a solution of just acetate. So you pair it with a neutral cation, like a group 1A, group 2A, and then you've gotten your weak base into solution. And finally, we're going to look at rubidium sulfate, so the RB there and the sulfate. So RB, not a common one, but this is in group 1A. Not something we see a lot, but it is in group 1A. Group 1A cations are always neutral. So that leftmost part of the periodic table, that's why we use those ions a lot. They are always soluble and never affect the pH of a solution. So they're very useful in the lab when you want to just make a salt that is soluble that does not affect the pH. Or more importantly, you want the other side of the salt, like the anion, to affect the pH. Rubidium, sodium, lithium, they can dissolve. The salt will be very soluble, but importantly, it itself will not affect the pH. So then the question is, SO4 2-. It's an anion, so it may be a base. And so the conjugate acid will determine it. And we want to be careful here. HSO4 2-. The conjugate acid is HSO4-, not H2SO4. HSO4- is a weak acid, which means this is a weak base. So sulfate is a weak base, and this salt is basic. So we really want to be careful. This salt is basic. You may be tempted to say that the conjugate is H2SO4, which is strong. But the difference between SO4 2- and H2SO4 is 2 hydrogens. So this is not a conjugate pair. This is the conjugate pair. And HSO4- is a weak acid. It's pretty good as far as weak acids go, but it is still a weak acid. So sulfate is a very weak base, but it is still a base. It is still a weak base, and rubidium sulfate, if you dissolve this into water, will have a pH that's greater than 7. It may only be like 8.5 or 9, very small change in the pH, but it will still be that. We want to be careful. H2SO4 is the strong acid, but this is not a conjugate. Because that difference is 2 hydrogens. 1 hydrogen is the difference we'd be looking for. Because this is a weak acid, this has to be a weak base. Rubidium sulfate is a basic salt.
Some ions can be tricky. So for example, amphoteric ions like H2PO4-. It has H's in the front, so it's a weak acid. This thing can donate hydrogens. It is a weak acid. It's also an anion, and the conjugate is a weak acid, so this thing is also a weak base. So in water, this molecule, H2PO4, can react with water to produce either or both hydroniums and hydroxides, right? So both of these can happen. And so what does it do in water? How does it affect the pH? So actually calculating the pH is not pleasant. It's a decent to do. But for us, what we can at least say is that we would expect it to be acidic. So it will lower the pH. If you put H2PO4- in solution, the Ka you can see is 10 to the -8th, whereas the Kb is 10 to the -12th. Because Ka is greater than Kb, what that means, how we can think about it, is that H2PO4- is a better acid than a base. It's weak in both, but it's better at being an acid. It's actually a pretty bad weak base here. And so if you were to dissolve it in solution, it would lower the pH. We don't need to worry about calculating what the pH is. We just want to know that it will lower the pH. You can also have issues where you can have a mixed ions in a salt. So for example, ammonium hypochlorite, NH4ClO. When that dissolves, you get ammonium, which is a weak acid, and hypochlorite, which is a weak base. So both of these are in solution, and the question then is this overall going to increase or decrease the pH? And so again, we turn to the Ka and Kb's of these values. So we can see the Ka of ammonium, 10 to the -10th, the Kb for hypochlorite, 10 to the -7th. Because the Kb of hypochlorite is bigger, that is a better base than NH4+ is an acid. So it is stronger as a base, meaning that we would expect overall this would be a basic solution. this is going to be overall basic because the base that's in the solution is stronger than the acid. So it would have a larger effect on the pH. You would have a net increase in hydroxide. So it's a lot about kind of parsing out what's the strong of if you have this kind of conflict, what is stronger among them. So it's about, again, using those dissociation constants, looking them up like we've done previously. So when we are parsing out acidity, we want to be able to identify something as a weak acid or a weak base, need to use the table, find its conjugate, comparing relative strengths of things. We really want to be using our reference values of Kas. So here is a table that's on slide. You can also, there's tables posted on Blackboard. I would encourage you to use those tables, get the Ka values out of there, and work with those. The final kind of complication is when we are dealing with any metal cation that is from the main group or transition metal. And so what happens is these cations, when they get into water, they start to interact with the water and they form what are called complexes. And those end up being acidic. And so one of the things you'll remember that for metal cations, group 1A and group 2A, those are neutral. Group 1A and 2A cations are neutral. All other metal cations are acidic in solution. So it is kind of crazy because, you would think if I just told you it was Al3+, there's no hydrogens there, so it probably wouldn't make it acidic. You wouldn't think it's an acid. But what ends up happening is they form these complexes like this, and that complex is an acid. And the Ka for that one isn't even that low, right? 10 to the -5th. That's not too crazy. The pH is going to be noticeable. So whenever you dissolve aluminum cations in solution, in aqueous solution, the pH goes down. So transition metal ions, main group metal cations where aluminum is on the periodic table, those cations are always acidic. Only group 1A and 2A are not acidic.
Participation 3.3, question 2. Classify the following salts as acidic, basic, or neutral. Ki, ZnCl2, and NH4,2CO3. This is the second question on participation 3.3 due Tuesday, March 3rd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, classify the following salts as acidic, basic, or neutral: potassium iodide, zinc chloride, and ammonium carbonate. Okay. There was a participation question in this video. Participation 3.3. And there's one more video in this set. Maybe there'll be another question there. Who knows? Let's watch the video and find out.